Hello everybody. So I just discovered that some of the videos that I've done with derivatives only have audio in the left channel. I am sorry about that, but no longer an issue. I have fixed it. So all videos from here on out you should be able to hear in both left and right channels. Can you hear me? Can you hear me? All right. Let me do this. Let me do this. Okay, let's get started. Anyway, constant multiple. So first, I'm gonna do an example first. Okay. This and the sum rule, they're all really simple. So I think it's good to kind of just show you an example first. Because it's just not that bad. So here we have 3 multiplying x squared, we have 4 multiplying x to the 5th, and 10 multiplying x to the 7th. Okay, now the constant multiple rule is super simple. Okay, so if you want to take the derivative of this thing, if you want to find the slope at any point of this function, this 3 is just going to multiply out front. In other words, if I take the derivative, it's going to be 3 times the derivative of x squared. Okay? Plus 4 times the derivative of x to the 5th. Minus 10 times the derivative of x to the 7th. Okay? So this is all just notation. Let's actually do it, right? The derivative of x squared, power rule, right? Take the 2, bring it down, reduce by 1. So we'll get 3 times 2 times x to the power 1, which is just x. Plus, so that's the sum rule, right? Plus, and now we do this one, 4x to the 5. So the 5 is going to come down. 5 times 4, order of multiplication doesn't matter. And then the exponent is going to be reduced by 1. 5 minus 1, 4. Minus, and then 10 multiplies out front. 7 comes down from the power rule. And then x, and then 7 minus 1 is 6. Okay? So now, we could just do some cleaning up, right? 3 times 2 is 6. Plus 5 times 4 is 20. Minus 10 times 7 is 70. Okay? So, that's the example of the constant multiple rule. I know that this is a power rule example, but this applies to any function in the world. So now, kind of like last time, let's go through, sort of the proof of it. So let's say we have a function g, and g is any number, k, times f. Okay? And so, if we want dg dx, we want the derivative of g, that's going to be the limit as h approaches 0, g at x plus h minus g at, minus g minus g at x over h. Okay? And g at x is given. G at x plus h we can easily find is going to be k and then times f at x plus h. So now we can plug this in, right? We can plug everything in. We have g of x plus h, we have g at x. So let's plug everything in. dg dx is going to be the limit as h approaches 0. And then g at x plus h, that's k times f at x plus h. Minus g at x is k times f at x over h. Now, notice this. Notice Notice that the k we can factor as a greatest common factor from the top. Sorry. Okay, good. So we have the limit of a constant times a function, and the limit depends on h. So we can take that k and bring it out front. So we get k times the limit as h approaches 0 of f at x plus h minus f at x over h. And this whole expression now, this whole thing is the derivative of f. So we get k times df dx. Or again, you can write that as k times f prime of x. So in other words, all we got to do, if we have a constant multiplying a function, here's a constant multiplying a function, we just take the derivative of the function part and then multiply by the constant at the end, which is exactly what we did here. The function part is x squared, derivative of x squared is 2x, and 2x times 3 is 6x. Here, the derivative of 4x to the 5 is going to be, well, let me say that again. Say it differently. 4 times x to the 5, its derivative is going to be 4 times 5 times x to the 4, which is 20x to the 4. And then we're going to have 10 times 7 times x to the 6. Boom, there we go. So here's the example. Here is the proof. And again, this applies to any function in the world. Blair out.